Hi, this is Tzvi Rosen with another lecture on matrix theory. This time we're going to talk about vector spaces and subspaces. First, let's recall what we defined in one of the earlier lectures, which is transformations. And these were our interpretations as matrices, as functions from Rn to Rm. And Rn, at that point, we described this as the set of n tuples of real numbers. So we had a1, a2 up to an, where all of these a's, and I'm going to list it as ai, is a real number for all I. And these curly braces and the colon is set builder notation, which you can look up if you haven't seen before. Rm, on the other hand, is very similar. Let's give it a different vector name. So it'll be b1 to bm. Okay, so these are m tuples, so lists of ordered lists of m numbers, where each of these bi's are real. Bi real for all I. Okay. So what we're going to do in this lecture is to consider what type of object these Rn and Rm are. In particular, we're going to define a vector space as a set with two operations first is going to be addition, and second is going to be scalar multiplication. Satisfying some axioms. Okay. Let's get this special color. Put that in red. Oh, no. Okay. Okay, so what do we mean by axioms? So an axiom is a property that we require our system to satisfy. Okay, so in the case of a vector space, a vector space, or rather a set satisfying all the axioms will be a vector space. If it fails some axiom, it is not a vector space. Okay, pretty straightforward. Okay, so what are the axioms we're looking at? Well, there are a bunch of them, and here they are from the textbook, Anton and Ruris. So we have 10 axioms, and these are all related to our set V. So for the purposes of these axioms, we have this bold U and bold V are going to be elements of the set capital V. K is going to be a real number. And same with M. Let's put both of them here. Okay. And then this is the list of axioms they'll satisfy, and you can roughly break it down into the first 5 and the last 5. So we'll do that now. First, we have our axioms for addition. Number 1, if u and v are objects in V, then u plus v is in V. Okay, so that means that I can add things together and I stay within my set. This is called closure under addition. Because, like if a box is closed, even when you move around inside, you'll stay inside the box. So that's the idea here. You take two things, add them together, you're still inside the box. Okay, 2u plus v equals v plus u. That's commutativity of addition. Number 3 says u plus v plus w equals u plus v plus w. So that's called associativity of addition. Basically, when you're doing two different additions, it doesn't matter which one you choose to do first. You could group the first two together first or the last two together first. So you can associate the middle one with whichever one you want first. Okay, number 4, there is an object 0 in V called a 0 vector for V such that 0 plus u equals u plus 0, which is equal to u for all u in V. So this is called the additive identity. Okay, and we spoke about this a bit when we talked about the identity matrix. This is something that doesn't change anything when you add it. Okay, so you add it, a plus u stays a. Sorry, a plus 0 stays a. Okay, and we want to think about it only in terms of this property. So you don't want to immediately assume we're talking about a vector that has zeros in it. Instead, think about whatever this 0 is. It's a mystery for now, but it's going to have this additive identity property. Okay, number 5, for each u in V, there's an object minus u in V called a negative of u, such that u plus minus u equals minus u plus u equals 0. And here, this 0 is a reference to the additive identity. Okay, so this is called additive inverses. Okay, and the minus sign doesn't immediately mean we're talking about something whose coordinates are all negative of the other coordinates. That will generally be the case. But what we're talking about is something that is the additive inverse, meaning you add it on and you get your 0 object back. Okay, those are the axioms for addition. Now we have some axioms for scalar multiplication, which is the other operation we have. So if k is any scalar and u is any object in V, then k times u is in V. So this is closure under scalar multiplication. It's the same idea as the closure under addition, just using the other operation. Okay. 7, k times u plus v equals ku plus kv. So this is a distributive property. So scalar multiplication, let's put it this way. Scalar multiplication distributes over addition. Okay. I might start calling scalar multiplication SM. Okay, so number 8, k plus m times u equals ku plus mu. So I guess this should really be scalar multiplication distributes over addition, and this would be that multiplication by a vector distributes over scalar addition. Okay. So multiplying that vector on the right, you can do that separately with each scalar, or you can combine the scalars first and then multiply. 9, this is that scalar multiplication is associative, so it doesn't matter if I multiply scalars first, or if I multiply well, you know what, that's probably more like scalar multiplication commutes with multiplication of scalars. And when I say scalar multiplication, I mean scalar multiplication by a vector commutes with multiplication of scalars. So it doesn't matter if I multiply the scalars first or multiply by the vector first. And number 10 is that if I multiply the real number 1 by a vector, then I get the same vector back. And this tells me that 1 is the multiplicative identity, or the scalar acts like the scalar multiplicative identity. Okay, when you multiply it by a vector, the vector doesn't change. Those are axioms. It sounds like a lot, but most of them are pretty intuitive. You don't often have to check all of them. Sometimes it's just important to check a few, depending on context. Yeah. If you don't know anything about the system, you should check every axiom, but sometimes there are things you can assume about your system. So how do we show something is a vector space? So given a set V with operations plus and scalar multiplication, how do you check that it's a vector space? So check every axiom. Prove that they're satisfied. Prove that they hold. And the result, and that indicates that V is a vector space. How do we show something is not a vector space? All you have to do is find one axiom that fails to hold. If any one of those axioms fails, then the set is not a vector space. Okay. Let's consider an example and demonstrate it as a vector space. So we have R3. This is the set of ordered lists of numbers A1, A2, A3, where these are all real. Okay, so in order to confirm that this is a vector space, we want to show that it has all of the desired properties. So first up, we have closure under addition. Okay, well that's easy enough, because if I have two vectors, A1, A2, A3, and B1, B2, B3, this is going to be equal to A1 plus B1, A2 plus B2, and A3 plus B3. And since all of those are real numbers, this is also in R3. Okay. In terms of the other axioms of addition, 2 and 3 hold automatically. Okay, and now we have to confirm that we have an identity and an inverse. 2 and 3 hold by properties of real numbers. 4, we need a 0 vector. Our 0 vector will be the vector with all zeros. Okay, because when we take A1, A2, A3 plus 0, 0, 0, that's just going to be A1, A2, A3 again. And the same would be if we added it in the other order. Okay. How about the additive inverse? Okay, so if U is equal to A1, A2, A3, we're going to take minus U to be equal to minus A1 minus a2, and minus a3. Okay, this is our definition. Then u plus minus u, which is the same as minus u plus u, will be equal to a1 plus a1 minus a1, let's say, a2 minus a2, and a3 minus a3. That ends up being the vector of all zeros, and we just decided that this is our 0 vector. So that means that minus u is a valid additive inverse. Okay? Great. Now let's think about the scalar multiplication axioms. So if we start with 6, closure under scalar multiplication. Then we can consider k real numbers and u a vector a1, a2, a3. Then ku, which is k a1, k a2, and k a3. Well, since k is a real number and all of the ai's are real numbers, all of these guys are also real numbers. So that means that ku is in R3. By the way, this symbol, in case you haven't seen it before, just means in. Okay. Okay, now we need to check distributivity properties of the scalar multiplication. So let's recall what those are. So first of all, k times u plus v distributes, and k plus m times u distributes. And then we have associativity and identity. Okay, so we have, so 7 says k times u plus v equals ku plus kv. So how would I go about proving this? Well, you just spell out what these vectors are. So on the left-hand side, we have k times a1, a2, a3 plus b1, b2, b3. Okay. So then we want to add it first and then multiply k. So we get k times a1 plus b1, a2 plus b2, a3 plus b3. And distributing, we get k a1 plus b1. Okay, or actually, sorry, we're not distributing. We're just multiplying in the vector, in the scalar into the vector. So it's k times a2 plus b2, k times a3 plus b3. Okay, so that's our vector. And now we can use distributivity of multiplication of real numbers, okay, because we're just looking at a bunch of different real numbers here. So this is equal to k a1 plus k b1, k a2 plus k, b2, k a3 plus k b3. Okay. But now this looks a lot like an addition of vectors, and I can pull it apart as k a1, k a2, and k a3 plus k b1, k b2, k b3. And what we notice is this is exactly ku, and this is exactly kv, so we have ku plus kv. So what we've shown here is this is the left-hand side, and this is the right-hand side. So just by doing allowed operations, we showed that the left-hand side is equal to the right-hand side. Okay, and you can show similar equalities for 8 and 9. Basically, you follow the operations on the left-hand side of the equation, follow the operations on the right-hand side of the equation, and you show you end up at the same place. As for 10, we just want to check that 1, the real number 1, times u is equal to u. And indeed, So if we take any vector, so u equals a1, a2, a3, then 1 times u equals 1 times a1, a2, a3, which we can multiply in one coordinate at a time. We have 1a1, 1a2, 1a3. But because 1 is the identity in real numbers, in real multiplication, this is just a1, a2, a3, which is equal to u. OK? So with the exception of 8 and 9, which I'm leaving to you as an exercise, we've proven that R3 is a vector space with the addition and scalar multiplication that we're using. Okay, we checked all the axioms, or almost all the axioms, and we verified that this is a vector space. Let's look at another example. So this is R greater than or equal to 0. What I mean here is we're going to, instead of taking a vector with 3 coordinates, the set here is just, I'm going to switch back to blue. This is just the set of real numbers, A, where A is real and greater than or equal to 0. Okay, so we're not looking at negative numbers. Okay, now let's look up at our list of axioms. Are there any of these that seem unlikely to hold in this set? Okay, hopefully you're saying probably number 5 won't hold. For each u in v, there's an object minus u in v called a negative of u such that u plus minus u equals minus u plus u equals 0. Well, in R greater than or equal to 0, none of the numbers are negative, so we're going to have some problems here. So for axiom 5, okay, so there's the number 1, for instance. So 1 is a vector in this case, is an element of R greater than or equal to 0, but there is no minus 1 such that 1 plus minus 1 equals minus 1 plus 1 equals 0. This is because negative numbers are excluded. Okay. Another axiom that actually fills here is one of the axioms for scalar multiplication. So just looking at number 6, closure under scalar multiplication, what happens if we take a negative number and we multiply it by our vector? Let's get this bit more room. So closure under scalar multiplication, if we take minus 1 times the vector 1, this is not an element of R greater than or equal to 0. So it's not closed under SM. Okay, so this fails to be a vector space for at least 2 of the axioms. Okay, let's consider real valued functions. So here what I mean are functions f which take real numbers and map them to real numbers. And the way that we add 2 functions together we get another function whose values are always, so if you have x in R, that means that f plus g of x is just equal to whatever you would get by evaluating f and then adding whatever you would get by evaluating g. Okay, so that's how you get a new function by adding two functions together. And similarly, kf, so scalar multiplication, r to r, this is k times f of x will give me, k of kf evaluated at x is another function which you just evaluate by taking k and you multiplying that by f of x. So there's a straightforward way to define addition of functions and scalar multiplication of functions. And in fact, this is a vector space, all right? You can check that it's closed under scalar multiplication. Okay, so closed under scalar multiplication. Sorry, it's closed under addition, we should start with, based on what we just wrote, since if you start out with a function that has real values, the sum of the functions also has real values. Let's check the axioms. So we have commutativity and associativity of addition. Those we just get from the, so 2 and 3, commutativity and associativity, we get as kind of a consequence of just the addition being commutative and associative at each point, right? So once you evaluate the functions, it doesn't matter which way you're adding those values, or yeah. This is kind of inherited from the real numbers, from real addition. Okay. In terms of the zero vector, what would that be? Well, we want a function that, when we add it to any function, doesn't change it. But that's what that means. So let's call this z. This is a function z from R to R. So if f plus z, the function, is equal to f, that means that at any point, f plus z of x is equal to f of x. But we know that this is defined as f of x plus z of x. But if f of x plus z of x equals f of x, that means z of x is equal to 0 everywhere. So the 0 vector in this vector space of real valued functions is going to be the identically 0 function. Okay, how about the additive inverses? Well, you can take, so additive inverse, just take minus f, let minus f of x be the function g of x, which always just takes the negative value to f of x. Whatever f of x is, multiply that by -1, and you've got your inverse. Okay, pretty straightforward. In terms of scalar multiplication, so the closure under scalar multiplication, you've got automatically under scalar multiplication basically comes by definition. 7 through 9, these are all just consequences of how this works. You're basically just multiplying the scalar at a point, at every point. Seven through 9. Multiplying scalars at each point. So it's basically inherited from the real numbers. And as for the the scalar multiplication identity, so 1 is the identity of scalar multiplication. That comes just by definition of the scalar multiplication. 1f of x is equal to 1 times f of x, which is just f of x everywhere, so that's just f. Okay? So we've confirmed that this is also a vector space. Okay, so this is already a little more complicated. This, it's not just R3. This is a very complicated vector space. It has a lot of stuff in it, a lot of different possibilities. Sometimes you can define a vector space where it looks super weird. It doesn't look like a vector space that you would be familiar with, and yet it satisfies all the axioms. And a good example is this. So here we're going to let our vector space V be given by the set of real numbers. Okay, so 0, pi, anything like that is in the set. Okay, and the addition is given as follows. So taking a plus b, so if a and b are in V, we define a plus b in terms of the vectors, the vector addition, to be to be the multiplication of the real numbers. Okay. As for scalar multiplication, so k in the real numbers and a in V, we define scalar multiplication ka to be a raised to the kth power. Okay? So raise a to exponent k. And believe it or not, this actually satisfies all of the axioms of a vector space. So I'll just do a few of them. I don't want to prove all of them. So first off, you can see that if a and b are in V, then a plus b, which is just defined to be ab, well, this is also a real number. So we're closed under addition. Okay. How about commutativity of addition? So if we have a plus b, is that equal to b plus a? Well, this is ab, and this is ba, so it's commutative because real number multiplication is commutative. So this is true because real multiplication commutes. Okay. How about the 0 vector? Okay, we'll skip associativity for now. The 0 vector, we need a vector which, when you add it to any real number, you get the same real number back. So a plus 0, I'm going to put a little line under it so we know we're not talking about the real number 0. We're talking about the vector 0. Okay. So, oh, you know what? This should probably be positive real numbers. That's important. Positive real numbers. So real numbers greater than 0. Okay, so we need a number a plus 0, which is equal to 0 plus a, be a. But the way that this is defined is a0, right? So whatever this 0 number is, we're going to be multiplying it by a, equals 0a, which will be equal to a. So this is describing a multiplicative identity. So 0 must be a multiplicative identity, So it's going to be the real number 1, right? Implies that 1 is the 0 element. Okay. How about additive inverses? So how do we determine what minus a is here? Well, we know that a plus minus a is supposed to be equal to the 0 element, but the 0 element is 1. Okay, and the way we would add a and minus a would be to multiply them. So a times minus a would be equal to 1. So this means that minus a is really equal to 1 over the real number a. Okay? When you multiply that by a, you get 1 back. So that corresponds to being an inverse under vector addition. Okay? It's kind of weird, but so far it works. Okay? Let's do a couple of scalar multiplication axioms. Do that in green. So closed under scalar multiplication. Okay, so this is one of the reasons I needed to correct myself that we're only using positive numbers as our vectors, because we need to have a well-defined exponent. But if a is a positive real number, then a to the k is a positive real number for all k real. Okay, so it is closed under scalar multiplication, the way we're defining scalar multiplication. How about associativity or the distributivity? So let's try to do the following. What if we have k times u plus v? We want to show that this is equal to ku plus kv. Okay, well, we have to remember how we define these things. So u plus v is going to be the product of the real numbers u and v. So that's uv times k. So this is the left-hand side. And this is going to be equal to uv raised to the kth power by definition of the scalar multiplication. But then if we're talking about uv raised to the kth power, now we're in normal real arithmetic. The exponent distributes. So this is u to the k, v to the k. But that equals ku, k scalar multiplication u, times k scalar multiplication v in this weird system. And that's equal to k dot u plus k dot v once we translate to this weird vector addition. Okay, and that's the right-hand side. So we verified this identity. Okay, again, weird, but it works. Finally, we just want to check that 1 is our unit, is the identity for scalar multiplication. And indeed, when we have when we have 1 dot u, this can be understood as u to the 1 power. That's obviously just u based on our rules for exponents. Okay, so this was a thoroughly weird vector space, but it's a vector space nonetheless. Fortunately, we're not going to work with this type of vector space very much, but it's good to be familiar with it. Here are a few properties of vector spaces that we can infer just from the axioms. We'll start with the first one. This is saying that taking the real number 0 and multiplying it by any vector will give you back the 0 vector. Okay, meaning the vector which has the properties of the additive identity. So how can we prove this to be the case? Well, we know that u has to be equal to 1 times u by the property of 1 as a multiplicative identity for scalar multiplication. Okay, so 1 is the identity for scalar multiplication. But then 1 is equal to 1 plus 0. And then by distributivity, I can split this up as 1u plus 0u. Okay, and this is the distributive property. Now, with 1u plus 0u, I now have a series of equations that tells me that 1u is equal to 1u plus 0u. Okay? Now I can add to both sides of this equation the additive identity of 1u. Sorry, the additive inverse. So I have minus 1u plus 1u is equal to minus 1u plus 1u. And we know these inverses always exist. Sorry, plus 1u plus 0u. Okay, and so that gives us things that will cross out. And we're left with, and this is by additive inverses. And we're left with the 0 vector on the left-hand side and 0 plus 0 times u on the right-hand side. But we know that 0 added to anything just gives you the same thing back, so this should be equal to 0 times u. And that proves property 1. Okay. We can do a similar argument for number 2. K times the 0 vector should be equal to the 0 vector for any scalar k. How do we know this is true? Well, we want to show that k times 0 will have the properties of the additive identity. Well, we know that k times 0 plus v should be equal to k times 0 plus k times v for any vector v. Okay, and that's by distributivity. But if we have k times 0 plus, we know that k times v, we know that v is equal to 0 plus v. So that means that kv is equal to k0 plus kv for any v. Well, then we can add the additive inverse of kv on either side. Okay, so minus kv plus kv equals k0 plus kv plus minus kv. And then we deduce that these things cross out. Okay, we know that these are available by virtue of the additive inverse. And what we're left with is that k0 is equal to the 0 vector. Okay? Now let's think about minus 1 times u being the minus u vector, the additive inverse. Well, this one is about as straightforward as the others. Think about what 0 is equal to. 0 is the same thing as 1 plus, sorry, now I'm talking about the scalar 0. This is the same thing as 1 plus minus 1. We saw above that 0 times any vector is equal to the 0 vector. So 0 times u is equal to 0. But we can also split this up as 1 plus minus 1 times u. Okay, this is from property 1. And by distributivity, this is equal to 1u plus negative 1 times u. Okay. We know that 1u is just U by virtue of the fact that 1 is the identity. So this comes from distributivity, and that 1 is the identity for Sm. So what we learn is that 0 times U, which we saw earlier is equal to 0, is also equal to U plus minus 1 times U. Implies that U plus minus 1 times U equals the 0 vector, which means that minus 1 times U is the additive inverse of U. Okay? And just one more. If Ku equals 0, then K equals 0 or U equals 0. Well, Ku equals 0. So we're going to take it a case at a time. So suppose K is not equal to 0. Then it's a real number that's not equal to 0, so there's a number K inverse, or 1 over K. So multiply both sides by 1 over K. Then we get 1 over K times Ku equals 1 over K times the 0 vector. This is equal to 1 over K times K times U by one of the axioms of scalar multiplication. And this is equal to 0 by property 2. Okay. And this is equal to 1. So we have 1 times U, which is just U, is going to be equal to 0. Okay, so what we've shown here is if we suppose that K is not 0, that means U is 0. So that tells us that either K is 0 or U is 0. Okay. So that proves all of those properties. Throughout all of those proofs, we're using the axioms, not assuming anything about the structure of Rn or anything like that. We're just using the vector space axioms. Okay. Now we're going to describe subspaces, which are the first important structure that you get to when talking about vector spaces. And a subspace is very simply a vector space inside of another vector space. Okay, so if you're given a subset of a vector space and you know what, I'm going to start writing VS for short, is a subspace if it satisfies all of our axioms, but most of the axioms come for free from the fact that it's a subset of a vector space. The only ones that don't come for free is it has to be closed under addition and closed under scalar multiplication. Okay, those are the only ones that you have to prove to show that a subset is a subspace of your vector space. In particular, so let me give myself a bit of room here. So if we have vectors u and v in W, that means that u plus v has to be in W. And by the same token, u in W and k real means that ku must also be in W. Okay? So not every subset of a vector space is a subspace. We'll see examples of both subspaces and non-subspaces. So first easiest example is the zero subspace. So the zero subspace of any vector space. So we know that every vector space has a zero element. That's one of the axioms. So if I just take 0 to be my subset, this will satisfy all of the axioms of a vector space, including the closure, right? Because if you have 0 plus 0, this is just equal to 0, which is in W. So that means that it's closed under addition. As for k times 0, we know that that's equal to 0. That's one of the properties we proved. So it's closed under scalar multiplication. Okay, so this is a subspace that you're always going to find. Okay, now let's get a little bit more detailed. So we want to have vectors in R3 that add up to 0. So in particular, we're looking for A plus, so it'll be vectors of the form A1, A2, A3, such that A1 plus A2 plus A3 equals 0. Well, how could I show that this is a subspace, or not a subspace for that matter? Again, you just need closure under addition and closure under scalar multiplication. So take two vectors, u and v in, so we're going to call this W. Okay, we'll write that here. Okay, u and v in W, then we can say the u is equal to A1, A2, A3, and v is equal to B1, B2, B3. And we want to see if u plus v is in W. So let's spell it out. U plus v equals A1 plus B1, A2 plus B2, and A3 plus B3. The sum of these, we want to check if it's 0, because in order to be part of W, I need to have all of my coordinates add up to 0. Well, the coordinates of u plus v are A1 plus B1 plus A2 plus B2 plus A3 plus B3. But this is equal to A1 plus A2 plus A3, which is equal to, and plus B1 plus B2 plus B3. And we know that since u and v are both in W, this has to add up to 0, and this has to add up to 0. Okay? So that means that this will also be 0, which tells us that this is closed under addition. Okay, so this means closed under addition. How about being closed under scalar multiplication? So we need to consider k a real number and u and w. Okay, so u as before is going to be A1, A2, A3. And we know that A1 plus A2 plus A3 equals 0. Well, what happens when we compute ku? That's equal to ka1, ka2, ka3. So when I add up the coordinates here, I get ka1 plus ka2 plus ka3. And I can factor k out of that. And I get k times A1 plus A2 plus A3, which is equal to k times 0, or just 0, right? Because A1 plus A2 plus A3 is 0. So that tells me that W is also closed under scalar multiplication, so it's a subspace. Okay? So all of the vectors of this type live in the same subspace. Okay. So we spoke earlier about the set of all real-valued functions. Let's consider a subset of that set. Okay, so this is inside in the space of real-valued functions. We're going to name this W. It's the one that, so W is the space, the F, such that f of 1 equals 0. Well, is this closed under addition and scalar multiplication? So if f and g are in W, that means that f of 1 equals 0 and g of 1 equals 0. So when I add them together, f plus g of 1, that's just equal to f of 1 plus g of 1, which will also be equal to 0. Okay, so it is closed under addition. How about scalar multiplication? K in R, F in W. Then f of 1 is equal to 0. So k f of 1 is equal to k times f of 1. We know f of 1 is 0, so this is just 0. So we have closure under addition and under scalar multiplication. So that tells us that W is a subspace. Okay, so we've seen a lot of subspaces. I wonder if there's a non-subspace coming up. Okay, how about functions which are equal to 1 at 0? So W equal, this is a subset of the same vector space we were talking about before, the set of real-valued functions, space of real-valued functions. And now we're looking at f such that f of 0 equals 1. Okay, so just looking at this, I can tell right away this is not a subspace, because if I take f and g both in W, then when I add them together, so we know that f of 0 equals g of 0 equals 1. When I add them together, f plus g of 0 is f of 0 plus g of 0, which is 1 plus 1, or 2. So the sum of these two functions no longer lives in W. This means that W is not a subspace. Okay, and you could actually deduce this from the second property as well. If you multiply it by some scalar, then the value at 0 is going to also scale. And it's not going to be 1 anymore. It's going to be whatever scalar you introduce. Okay. So those were some subspaces as well as an example of a non-subspace. And the final topic will be linear combination and span. So if you have some collection of vectors, so given v1, v2 up to vn in a vector space, a linear combination of these vectors is W equal to k1 v1 plus up to kn vn, where k1 through kn are real numbers. Okay, and the span of v1 through vn, sometimes denoted by span of v1 to vn, is the set of all vectors which are linear combinations of v1 through vn. Okay. So linear combination and span are two important concepts. And oops. And the span of any set of vectors is a subspace. Of the vector space V. Okay. So let's do an example to think about the span of a certain set of vectors. So we want to know if the vectors 1, 2, and -3, and 3, -4, and 1 have the vector 1, -1, 0 in their span. Okay, so let's give that a shot. Well, we would need a real number A times 1, 2, -3, plus a real number B times 3, -4, 1, which would be equal to 1, -1, and 0. So let's figure this out. So one way to do this is to realize that, oh, you know what? This is actually a matrix multiplication. This is the same as 1, 3, 2, -4, -3, 1 times AB equals 1, -1, 0. Okay. So one way to solve this would just be to do row operations on the augmented matrix. So we could do 1, 3, 1, 2, -4, -1, and -3, 1, 0. And go ahead and do matrix row operations here. So we have -2 row 1 plus row 2, -3 row 1, sorry, it should be +3 row 1, plus row 3, and we get 1, 3, 1. This should be 0 and -6, this should be -10, and -3, and this will be 0, 10, 3. Okay, so clearly we can just ignore the third row because it's a restatement of the second row. But what this tells us is that -10 times b is equal to -3, which means that b is equal to 3 over 10. And a plus 3b is equal to 1, which means that a is going to be equal to 1 over 10. Okay? So that tells us that, and we can now double check our work. So this gives us 1/10 of 1, 2, -3 plus 3/10 of 3 -4, 1 should be equal to, well, 1/10 on top plus 9/10 is equal to 1. 2/10 second row plus -12/10, that should be -1. And then -3/10 plus 3/10 in the bottom row gives us 0, which is exactly what we wanted to come up with. So this is a linear combination of the other two, meaning it's in their span. Okay, well, how about the other one? So it's 0, 1, 1. So there, this would translate to a pair of real numbers where you have a, 1, 2, -3, and b is 3 times -4, 1. We want that to come out to 0, 1, 1. It's the same situation, we can use the augmented matrix, 0, 1, 1. But this time when we do our row operations, so we take minus 2r1 plus r2 and 3r1 plus r3, what we get is 1, 3, 0, 0, minus 10, 1, and 0, 10, 1. Sorry, that's, yeah. So here, when we do one more step of row operations, we get row 2 plus row 3. We now have 1, 3, 0, 0, minus 10, 1, and 0, 0, 2. This final row here tells us that the system is inconsistent, because you can't have a linear combination of A and B where both A and B, where both are being multiplied by 0, and yet you get 2 at the end. So this tells us that the system is inconsistent. So this vector is not in the span. Okay. And one final definition before we conclude. So we recall that a transformation is a map from Rm, or no, it's usually from Rn to Rm. So this is a matrix transformation. Okay, then T, the set of vectors in Rn, so the set of vectors V in Rn with T of V equals 0 is a subspace. We call this the kernel of T, or Ker of T. Okay. To prove it's a subspace, you would do the same thing we've been doing before. Think about what happens with a linear transformation when you add two vectors together that both get sent to 0, and then do the transformation on them. So I'll write this out here. Note, so T of V plus W is equal to T of V plus T of W by linearity. And the same holds for T of K times V. That's equal to K times T of V by linearity as well. So if T of V and T of W are 0, then so too will any sums or scalar multiples of them. Okay. So that's why the kernel is a subspace. Now let's try to compute the kernel of this matrix. So the kernel of this matrix is the set of vectors. So we have 1, 3, minus 2, minus 1, 0, 2. These are the vectors x, y, z, such that the multiplication by this matrix give us the 0 vector, which is 0, 0. Okay. Well, how would we solve this? One way to do it would be using the augmented matrix yet again. So we would have 1, 3, minus 2, 0, minus 1, 0, 2, 0. Doing row reduction, we get R1 plus R2 gives us 1, 3, minus 2, 0, 0, 3, 0, 0. Okay. And we can then scale this row. So we have 1/3 R1 gives us 1, 3, minus 2, 0, 0, 1, 0, 0. And now we can add the minus of the second row to the top row to get, so minus R2 plus R1 will give us it should be minus 3R2 plus R1, 1, 0, minus 2, 0, and 0, 1, 0, 0. And what this tells us, this final matrix we have, is that x minus 2z must be equal to 0, and y must be equal to 0. So if I want to understand what the kernel of this transformation is, I can say kernel of t is equal to the set of vectors t, or actually, this should be 2t, 0, t, where t is a real number. Okay? And plugging that in yourself, you can see that is in the kernel, and it also describes the entire kernel. Okay? And we'll play more with that in the homework and going forward in the course. Thank you so much for your attention.